Okay, I think we're gonna get started. Hey everyone, welcome back for the second workshop speaker event today. Now we're gonna have a structural engineering workshop with Miss Mary, who's a structural engineer. Do you want to introduce yourself to the audience before we get started?
Sure. I'm Mary Phung. I'm a registered licensed professional and structural engineer in the state of California. I grew up in Sacramento, which is about 2 hours north of here, and went to school in Sacramento. I graduated from UC Davis with a bachelor in civil engineering and have worked for over 15 years in the structural engineering field.
Okay, that's pretty cool. So let's just get started, I guess, with the workshop. So for those of you who don't know, or some people don't know, could you explain what exactly structural engineering is and how important it is in a community?
Yeah, what is a structural engineer? The way I like to describe our profession is we're very similar to the skeleton in our body. We're the framework. And within that framework, we design it to withstand seismic or earthquake and wind loading. So we make it safe and designed to ensure that our skeleton is strong and stable. So here in California, we're known for earthquakes, right? We have a lot of active faults that runs up and down the entire coast. So usually our design is governed by seismic. So unlike the East Coast, they're known to have hurricanes. So typically wind is what governs their design. So for comparison, hurricane wind forces is almost 5 times what it is here in California. And so for seismic design, the force is actually proportional to the weight of the building. So the heavier the building, the larger the forces induced on the building. So buildings made up of concrete or steel would have a greater force than buildings made up of wood or metal stud. So our role as a structural engineer is we design for life safety. So for example, schools and hospitals are designed to a level where it could still function and remain operational after even a seismic event.
Yeah, that's pretty cool. And it seems like it has a really big importance because it's like essentially the backbone of all buildings. So without it, almost everything would fail.
Right.
So yeah, so some of us have heard of like structural engineers and architects and how they're related. So could you explain the difference between a structural engineer and an architect?
Sure. Yeah, we often get mistaken as architects because when I tell people, hey, I designed that building, the first thing they say is, oh, wow, it's so pretty. But unfortunately, our work is actually covered up since we are that framework. We essentially hold up the building and the architect comes up and covers it up and makes it presentable. So the architect, I would say, is similar to the skin on your body. And we're the skeleton, they're the skin. And our role is more technical and analytical since we evaluate the actual performance of the building and analyze each members and how they are connected. So we put together buildings, we put together drawings that provides directions really to the contractor on how things are built in detail. And an architect is more in charge of the aesthetics. So an architect has a vision, and as structural, we make it possible and make it happen.
So since structural engineering seems like a very technical field, what do you think is the most important quality to be a successful structural engineer?
What is the most important thing that makes it? It's just learning, right? There's always something to learn because we have a code reference that we go by and so many materials to learn from. It's always constantly learning. So
Yeah, I agree. Learning is important in like almost every profession. So well,
right,
people who have like a will to learn usually succeed in whatever they're trying to do.
right.
And talking about learning, how do you work in teams? And if so, like how exactly do you explain who you work with and what sort of procedures you plan?
So when we start a project, we typically already have a whole team picked. We collaborate a lot with the architect, mechanical engineer, electrical engineer, plumbing engineer, geotechnical engineers, and contractors. We have weekly meetings to discuss our needs and how to assist each other. Before a project even starts, a geotech engineer actually goes out to the field and starts taking probes and take boring samples of the soil, so they could give us kind of recommendation on what type of foundation we could use. So here in the Bay Area, there are pockets of liquefiable or bay mud. So we really can't rely on the soil sometimes to support our building. So sometimes they'll come in and recommend a mat foundation or piles. And a mat foundation, essentially one big slab of concrete. So when the building settles, it will settle uniformly. And piles are more like a series of columns in the soil to support the building. So they're basically on stilts. So the geotech engineer is actually usually the first person we interact with to start our structural design. But throughout the project, we're always coordinating with the mechanical or plumbing engineer. And there are times when they want to come through and penetrate through our structural walls or members. So we have to coordinate with them to either shift around our elements or reinforce what we have. So each discipline provides their own 3D models. So and for structure, we design each member. And once we figure out the actual size, we input it. We have a drafter that comes in and inputs it into a 3D model. And then we share that amongst the team. See, the architect has their own model. And with that, they kind of lay out their rooms and where they want their offices or, or whatever they're designing for. And the mechanical will have their own model to how they want to run their duct works. And then once we're all done, we bring all the models together and we have what we call clash detection. And then, so for the architect, they'll shift their partition around our structure, and the mechanical will try to see where our beams are and when the architectural ceiling is and see if their duct can fit within that space. So we really take a project from beginning to end. There's a schematic phase where this phase is where we provide initial ideas to discuss what kind of lateral system we want and use and what's cost effective. And then there's the design development phase, where we develop the ideas in more details. And then there's a construction document phase where ideas are finalized. So then it goes to plan check when it's all done, which is really like a second pair of eyes that reviews all our calculations and details and drawings to make sure we're not missing anything. And then when it gets approved, then it starts getting built. And usually we're still involved with that with the contractor to kind of assist with any questions they may have on the drawings if issues arise. Because during construction phase, we're still coordinating because there's always some unforeseen issues in the field.
Yeah, wow, that looks really interesting. It looks like there's a lot that goes into each procedure. So when you're planning these like intricate projects, what's your favorite part throughout all these steps?
I really enjoy detailing for a project because I enjoy the intricacies and challenges of how things come together. Because of how involved detailing is, you kind of have a better understanding how critical that element is and the load path for the building. And the load path is really important because you're essentially guiding the seismic load to the lateral force resisting system, which is really that element that absorbs the building load. So it could be a concrete wall or a steel brace frame that's going to be taking that hit once, an earthquake happens. And that all has to go down to the foundation. So I really enjoy putting together a set of drawings. So if you ever play with Legos and you have those set of instructions, that's kind of like what we do. We basically are telling the contractor how it's built. So how many rebars goes in the wall, how many nails, what spacing, how big the bolts are, or size of members. That's what we're doing. And all that is really based on an analysis on how much force each element can take. And then when you get to the construction administration phase, you kind of have a better feeling of the capacity of your members. So if there is a need for a fix, we're ready for some kind of inventive ideas to solve it.
Yeah, so it seems like a lot goes into each project, even like the really small parts. So with all these like things going on, even though it might be difficult to designate a certain number value for this, but on average, how long does each project take?
Right. And that really depends on how big a project is and what type. So we have projects that we call design build type of projects, where the contractor is actually starting the process of building while we're designing in parallel. And that the full concept is still being developed until the very end. And the process is very fast paced, with the understanding that we'll still make up changes, but we'll end up doing it in the field fixes during construction. And then we have other project called for design bid build type of project, where the design is fully designed and then it goes out to bid, and then they have to see if they have enough money to build it. So for example, we're working on a 10-story concrete office building in Sacramento, and it's still in the construction phase, and it's slated to be done in October. We started around September 2018. So it's about 3 years. And that same 10-story project, if it was built under design build, can take twice as long. Other projects like designing homes or condos can last just a couple of weeks or a month. So it really depends on how big and what type of project.
Just out of curiosity, what's the longest project you've ever worked on?
Oh gosh. It could range from probably about 5 years, just because of how things are going, not construction wise. It could be other unforeseen political things.
Yeah, that makes sense. Also, just what's your favorite project you've ever worked on, and why was it your favorite?
I don't really have a favorite per se. I would say it's really just the satisfaction of driving or walking past a building I designed or was a part of, and seeing and hearing how people admire it. But every project is fulfilling because we're always encountering something different out in the field. We're always learning something new. And I've worked on a variety of different projects. I know there was one that it was a voluntary project, and it was where they turned an existing barn into an office facility. And the owner was using that building to kind of train puppies for wounded veterans. So projects like those are rewarding to me because, it kind of gives back to the community.
Yeah, I can imagine how impactful that would be. So also COVID-19 probably had an impact on everyone's lives and even work. So how much has it impacted your work as a structural engineer?
Yeah, absolutely. The pandemic kind of affected us. A lot of our new projects that we were bidding for got put on hold because some of the ones that were, and some of the ones that were in construction. The project in constructions that were deemed essentials were allowed to continue. So that 10-story project office building that I had mentioned before is next to the Capitol in Sacramento. And it was being built because they're going to eventually do renovation on it. So once they start adding an addition, all the employees will move into our building temporarily. And because it's a state building, it was deemed essential. So that's really where Gavin Newsom will end up staying. Also, due to the pandemic, it really affected the cost of materials and also the lead time to fabricate the materials. So it kind of had a domino effect. We had several projects where I know steel prices went up or the fabrication time would take months. So we had to end up going back to our design and redesigning it for like an entirely different system.
Yeah. Now let's jump back a little bit in time, all the way back to like high school. So starting from there and up to now, what's the path that you took to reach your current profession?
Oh gosh. When I was in high school, I'm sure it was hard to know what you're going to do for the rest of your life at, 17. I didn't know what I wanted to do for the rest of my life. All I knew was that I liked drawing and I liked math. And I knew very little what civil engineering did and knew maybe they worked on bridges. So I actually wanted to be an architect because, people knew architect draw. But there wasn't an architecture major at Davis. So I ended up going into civil engineering, thinking that it'd be maybe easier to transfer. I ended up going there and pursuing that path. And you have to take all the upper level math, upper level physics. And under the civil field in college, you end up taking different engineering classes. So they have like transportation, water resource, geotech, environmental and structural. And when it came time to actually pick an emphasis, I concentrated on structural engineering because it had buildings. I took more structural classes in comparison to the other specialties, and I ended up enjoying it. So I stayed. And after graduating college, I got a job working in a company that designed mostly residential homes and apartments, but it was mostly wood construction. So after a couple of years, I wanted to learn other materials, and I left and started a company at the company I'm at now. And we do a variety of different projects and using different materials. So I've worked on projects from elementary schools, colleges, prisons, juvenile detention centers, office buildings, fire station, police stations, and they could be made up of masonry, wood, steel, concrete. And with the focus in structural engineering college, you have to take all these classes to kind of understand the behavior of each materials. And after working for a while, the really next step to pursue your career is to get licensed. So you have to work under a licensed engineer for a couple of years to qualify to take the licensing exam. And back when I took the exam, it consisted of 2 days back to back of test taking, 16 hours per day. So for the professional license, it was 8 hours per day. So for the professional license, there are about 3 exams, the national exam. So there's an 8-hour test that tests on everything on the first day. And then the next day, they test you on seismic, which is 4 hours. And then surveying is the next 4 hours. But nowadays, they break up the section. They make it a lot easier. And then the professional license actually allows you to kind of stamp your own drawing, with the exception of hospital and school work. So you could always open up your own business and, do residential homes if you wanted to. And after you've received your professional license, you could always continue to get your structural license, which means you have to work under a licensed structural engineer. And again, this license involves another 16 hours of test taking, but it's more structural specific. This one has more essays and problem solving. And it's the only profession that requires 2 licenses in order to stamp public schools and hospitals. So with the structural license, you get to stamp those 2 specific entities.
So as a structural engineer, you talked about you work with a lot of diagrams and models and so on. Like you do a lot of drawing, like you mentioned, you like doing in high school. So do you think there's any diagrams you could share with us that you have on hand by any chance?
Sure. Let me share my screen. Okay, can you see what's on the screen right now?
I don't see it. Let me check. I think you should have the ability to share.
Let's see. Probably didn't. I forgot to hit share. That's why.
Okay, cool. Yeah, I can see it now.
Okay, so this is an example of what we get from the architect. As you can see, they kind of lay out all the offices and how they want everything. And we'll come in and we'll start laying out and putting in our columns. So this is really where these are really the support of our slabs. So this is a gravity design. So the red is kind of like where we put our support. And as you can see, sometimes they don't line up because the architect doesn't want columns in their doors or in the middle of their room. So this is an example of, this is that 10-story office building that I was talking about. And imagine there's like 10 floors of these. So not all the rooms will be in the exact same place. So it's really hard to try to get all these columns to stack. Fortunately, we were able to get the architect to allow us to do that. If you can see on the bottom left, those 2 yellow columns I highlighted because on the first floor was a conference room. So they couldn't line those columns next to those red ones. So because of that, this span of the slab got too large and we ended up putting concrete beams in place. These are our lateral force resisting systems that I was telling you about. And these are the actual seismic absorber. So when earthquake hits, these are the ones that are going to be taking most of the forces. Let's see. And then in the end, this is what we end up providing. This is PT tendons, and this is kind of layout of how they'll put the tendons. And the PT tendons are these tendons that they put in the slab. So after the concrete is cured, they'll pull it, and that helps kind of lift up the concrete slab to help support it. And then these are reinforcing more steel that we kind of put together. Again, the blue is our main core and seismic element. And these red lines, we add rebars. Again, these, I talked about how we have to guide the seismic force back into our lateral force resistance system. So we kind of use these long bars in the slab to kind of drag it back. And we call these collectors. And wherever there's like an opening, like that X that we kind of show, we have to put bars in to kind of prevent the slab from cracking. And then after that, we put this in a 3D modeling system. This way, when we finally figure out what the actual size is, we input it, and this way the architect and the MEP, mechanical, electrical, plumbing, can tell how big the sizes are, and they know how and where to route their stuff. Or if we have a column that's in the way and the architect doesn't like it, they'll be like, can you make it smaller or move it? The yellow that I highlighted, again, that was in the very beginning where I talked about the geotech and how this building itself was in Sacramento, and the soil wasn't very good. So they recommended that it be put on piles. So again, this is where the mechanical input their model. So this is where we start collaborating and doing clash detection. And this is a zoomed in, and you can see all their ductwork coming in. So in parallel, this is really our structural model. This is the analytical model. And then we take this, we input it, and we're applying a seismic force. And so then after we apply that seismic force, we kind of animate it. And this is what we call mode shapes. And the Mo shape is actually the unique system of vibrating at a natural frequency. So when the building is excited, this configuration is like the displaced shape. So, and then we start showing it in every direction. So this is really sort of, how the building will behave when an earthquake hits. Obviously, it's amplified. It won't move like this, but essentially, this is what we model. All right, and then you can see it kind of rotating like that because the building itself is not symmetric. So that's what we call kind of like a torsion in the building. And then with this model, this is how we figure out the forces in each element. And that's how we kind of determine the sizes of our beams and columns and how much rebars or we need. And then these are some of the pictures. This is where they're drilling the piers. Some of the foundation. This is just a lot of rebars that comes into here. This is when they start building the walls and the columns. And this is part of the wall. They actually do it on the ground. They pick it up and then they put it in place. And then the tendons, which are the blue ones, is what I was talking about. So once they pour the concrete and it cures, they pull it, and then that helps lifts up the slab. And then here are some of the fixes that we ended up doing out in the field. If you can see all those brown cans, those are either mechanical or plumbing. So they really, when they put them in there, it's really essentially a big hole in our diaphragm. So we have to end up, putting rebars around it. And then the gray is conduit. So you can see how congested the slab is. And sometimes it gets so congested, it's hard to put actual rebars in, which is what we need to help put our slab, lift our slab. And then this is the part of the column where it didn't get consolidated. So these are things that we encounter out in the field. So this, we have to end up chipping down to the actual rebar and making sure that it didn't get, that it's okay and it didn't get rusted or something, and then we'll have them grout it back. This plate, they actually forgot to put big collectors in, which are those red lines that I showed you. So we had to end up doing a fix outside of the slab. And then this is some of the phases of that work. And then this is the facade. So this is when they're kind of done, they'll put this on the outside. This is a precast in the windows. And then this is the view from inside the building, except the Capitol. And then this is the building itself. So they're structurally, I say they're almost done. So right now they're doing the finishing touches. So they'll go in and start routing all the interior mechanical and ductwork and putting in furnitures or finishes and ceilings. Another project, so interestingly enough about this building is that we recently had an earthquake back in early July. And I don't know if you guys felt it, but it kind of triggered a couple of smaller earthquakes in Sacramento. And some of the contractors were actually up on the 10th floor, and they actually felt it swaying back and forth. So it's really not until an earthquake occurs do we actually get to see how our building behaves. So here's another project you guys might recognize. It's the Visual and Performing Arts at the Evergreen Valley College. That bottom right picture is the view from Montgomery Hill Park if you're ever running there. And then this is the music building. So here, this one's made up of steel moment frames. So we start laying out where we want our lateral system. Luckily, they all stack. And as you can see, we really want it to be symmetric, but unfortunately, sometimes we can't because they have big holes on the other end. And then this is the elevation of those steel frames, moment frames. And these are the ones at the exterior and interior of the buildings that will take the seismic load. And this is during construction. Yeah. This is that long music building before they put that logo on. And again, this is the theater building. Steel moment frames. This is where we ended up putting a lot of the exterior frames. Here are some of the framework. So this is, I would say, the structural part of it, right? The braces and the gusset plates. And then, of course, the architect comes in and starts putting in the furnitures and making it presentable. And then they have the ribbon cutting. So, nope. That was it.
Yeah, that's extremely cool. So I'm just curious, after creating these diagrams, do you actually get to visit the construction sites like in progress, or do you do most of your work behind the scenes?
No, we actually, like I said, we take it from beginning to end. So once it starts construction, we probably go out in phases. Like when they start pouring concrete, we'll go out there during that time, or when they start, putting in rebars. But for that big 10-story building, because it was so fast paced, they wanted us to actually go out there twice a week to kind of facilitate and help with the construction and to kind of inspect. We don't really do, we kind of do a visual inspection, but they actually have inspectors on site that is actually watching them do it correctly every day.
Yeah, that's pretty cool. So since we're almost out of time, do you have any last words of advice or anything you want to say to the audience before we wrap up the workshop?
I would say take advantage of the resources you have now. Everything is available to you guys on the internet. Ask lots of questions. Go to events like this one if you're, if you are curious about what other professions do. I really commend that you guys are even having something like this to kind of get insights and in-depth knowledge of what professionals do. So, you can always find someone to shadow for a day, ask to do office tours if you want. But if you have a passion and you find it interesting, focus on your school and study. And when you get into college, join clubs, So.
All right, well, thank you for your workshop. I think everyone learned something new and it was really helpful, especially the diagrams. It was cool to like dive into exactly what you do and see like all the structures. So I think that wraps up the second workshop for today. Thank you so much for coming.
Thank you.
And we'll see you guys all soon.
Okay, bye.